to today's workshop Wednesday. Sorry for starting a bit late. We had a few technical issues, but we've sorted them all out. Last month, we had a workshop by Brian Howie, on internationalization. In case you missed that, you can find it on our YouTube channel. And uh, sorry, one second. Yeah, so you can catch that on our YouTube channel in case you missed it. Today, we'll be having Edward Njoroge taking us through algorithmic thinking, the why, the when, and the how. And how this will go is we'll have Edward's presentation. Then towards the end, we'll have Q&A. If you're on the call, feel free to type your questions into the chat. If you're on the YouTube live stream, feel free to post your questions on the comments there, comment section there as the live stream progresses. And really excited for this one. I know algorithmic interviews are a huge pain point for a lot of us as we're doing job interviews. And I'm very excited to see what you have, Edward. So take it away.
Thank you, Ryan. And I'm also really excited to be doing this. So I'll share my screen and then do a bit of an intro, and then you can pick it from there. So about me, I'm a software engineer, unsurprisingly, but I've been doing this for like 7 years, 4 of which I would call the professional bits. So all through my interest in software engineering, I've been like maintaining a keen interest in data structures and algorithms and algorithmic thinking as a topic. So I hope that at least by the end of this talk, you'll have gained something. I do have some of my social links. You can follow me at Coordinated. If you want to look through what I'm up to on GitHub, you can email me if you prefer that too, or Coordinated. So hopefully that makes it easier for you to remember. So what I hope we achieve in this session is mostly to learn what algorithmic thinking is and why we even need it in the first place, and why we are even able to do it. What does it mean really? And then we're going to learn how to apply it, how to learn and apply it, and then eventually we'll see when we should actually apply it. It's not all scenarios that calls for deep analysis and algorithmic thinking, so we'll get to see at least a number of those. So to start out, we'll take a somewhat of a philosophical take. I think most why questions tend to take this direction. So forgive whatever this is if it's not what you expected. But we'll try to understand it from first principles and engage me. So we're going to really ask what we do exactly as software engineers from the ground up, and why we are even able to do it. So if we were to go to the very basics and think about what we do, or what any of this is as a reality. So we are kind of some intelligent agents. We found ourselves in an environment that largely depends on our ability to predict the future. If I see a car come in, there's no reason why I should be able to predict. There's really no reason why I should be able to predict a car coming my way is gonna hit me. But an intelligent agent's ability to survive will depend on its ability to be able to predict that. So uh, that's like, I think, um, a fundamental principle to acknowledge about our reality. And then we also happen to be in a universe that allows cause and effect as a fundamental law. So what this means is, we're able to reliably have a set of actions lead to a certain set of consequences, somewhat reliably. So like if I drop an apple, it will fall and it will like actually land. Again, being very philosophical, there is no reason why this should even happen in the first place. It just happens to be. It could be by design or like by accident. That's not the question of the day, but it just happens to be that way. So yeah, again, as I said, you're almost guaranteed a mapping between a set of actions to a specific set of consequences. And luckily, we are not blind to this cause and effects as law of nature. So we're able to model um, these causes and effects within us mentally, and that way we are able to predict what certain sets of actions will lead to. So again, if I see a car coming my way, I'll like dunk, and that way, like I don't have to wait for it to happen for me to know what has to occur, right? Um, so this obviously dramatically reduces the number of attempts we would have to make in order to predict a particular event. If we were not able to simulate this, I would imagine we would have to place like several people in front of cars and then decide, like simulate that whole um, event, like place them there, see what happens when they stay put, see what happens when they move 1 inch to the left, and all that. But luckily, we're able to like model this in our brain, and we are able to avoid like the whole process of conducting experiments. So we're able to do this in our brain. Um, so two bottlenecks become somewhat evident in this approach, and one of these is like our mental capacity for information processing. So just how much exactly are we able to model and like simulate in our mind? So if it were possible, we could go down to the very uh, low levels of our reality. Let's say atoms. We could simulate every atom, and that way we would have some very fine control over everything that we perceive. We would be able to predict how the wind would move even. But we kind of have a limited capacity for that. So over time, we've come up with like better approaches um, to solve that. And part of that was symbolic manipulation. So you can think of like writing out some X and Y values and then representing them and manipulating them in a way that follows how those mappings, the laws of those mappings, and then you're able to come to a conclusion. And then we also ended up having mechanical calculators and eventually electronic computers. So these are just ways of reducing that or like tackling that problem. So the next thing is the mappings and the models that we are using in the simulation. So um, we have to acknowledge that we are very lucky that we even have this, right, in the first place. But we also happen to be, there also happens to be many models or mappings that we could come up with in our simulation. So I'm trying to look for like a practical way of phrasing this. So I say I'm trying to think about the apple falling, right? And I could possibly start and like try and think about all the atoms that surround the apple as it's falling, because I mean there is air. I could think about the light that's hitting the apple, maybe that somehow affects the way in which it falls. There's so many things that I could account for, but there are things that I might not necessarily need to think about um, for me to conclude that the apple will hit a specific point, right? So that's just the model of simulation that you've decided to pick. And this is where like algorithms come in mostly. And so you have to like try, if you're trying to be efficient, you have to look for the best mapping that reduces the amount of energy and time that it will take to like compute them. Um, so again, that's like a bit of a philosophical take. Um, we'll go back to a more practical take, something that uh, makes more sense. Um, and so, like, if we go back to this, what do we do as software engineers? One of the things we do is, and I would imagine this is what majority of us do. It's what I do personally and what pays the bills. Um, we do automation through translating business rules into code, and the reason is um, manual transactions would have taken forever. So we're able to like just write those rules as a script, push it to some server, and then all the rules are like followed and like executed really fast. So yeah, that's mostly what we do. But within uh, within this practice of like translating business rules, uh, we've we've had to come up with like a substrate for like executing them, right? So like we need a place to execute them, and then we also need to have really good mappings, as we call them, that will save us on like the energy and the time it takes to compute these transactional rules. And so we end up having to solve certain algorithmic challenges within our work. And this is like the topic I hope we get to cover today. So yeah, we come up with solutions that are more efficient in terms of time and energy. So in CS, you'll talk about computer science, you'll talk about space more, but it's mostly about time and energy. Um, so, and it goes back to what we talked about as being able to maximally exploit the information a system gives you um, in order to avoid like spending a whole lot of time and energy that's not necessary to either compute something or like conclude something from a set of premises, while also respecting the constraints of like the underlying model of computation. We're going to break this statement down so that we like fully understand it. But if you were to be asked what algorithmic thinking is, this is what I'd say it is. So it's the practice of solving computational problems while maximally exploiting the information the problem offers, and addressing the constraints of the model of computation. So I think the three main components to this is the computational problems. What do we mean by maximally exploiting the information offered by those problems? And what exactly is a model of computation? So computational problems are problems that are solvable by sequential application of mathematical steps. Really, what this breaks down to, if I were to rephrase this, I would say it's problems that um, it's problems in our reality that can be solved by simulating the cause and effect rules offered by that by our reality. So I can like I can drop a ball and know that it drops. So it means if I had a formula that represents the rules that govern how that ball drops, I could take them and like create them in a computer, and then provide my parameters of where the ball is at, the gravity, and that way simulate, like just through calculation, simulate um, where the ball will fall. So that's a computational problem. And computer science, um, interestingly, resolves to computational problems, and it's just a whole lot of like computable functions, if you have to go down to the very basics. So the model of computation is, how are we going to compute those mathematical functions? What guarantees do we have? So like, what does it take to add one to one in our model of computation? So we need to understand the costs that are involved and the guarantees that our model of computation gives us. Um, so being maximally exploitative, or coming up with an optimal solution, um, is finding the solution that uses the least amount of resources in terms of time and space. We'll talk about space. I would much have preferred not to use space, but use energy. But while you're talking about computer science, we tend to think about time and space as the parameters. But space somewhat translates to the energy required. Um, so it's a measure of like complexity. So if you're able to reduce the time it takes and like the space it takes, then um, you're somewhat coming up with the most exploitative solution. Um, yeah. So um, I don't know if it would help to go back to that quote. Um, I think I should have maybe defined them before this, but um, you'll have a link to this, so you can still go back to it. So uh, at least now we know what algorithmic thinking is, why do we even need it, and why we are even able to apply it. Um, it was a bit of a spiel, but hopefully you've like gotten something from that. So the next bit that we're going to be covering is how do we learn and apply algorithmic thinking. Now that we know it's important, and um, we know why we need it in the first place, how do we learn it and like apply it? So the first thing to acknowledge is that there are no silver bullets. Um, we happen to be very lucky again, and I really would hate for this point to be lost on anyone. We happen to be very lucky that we are even able to do any of this. So the fact that we are able to simulate our reality, reliably simulate our reality, and like get results, it's you shouldn't take that for granted. And so um, having that in mind, and still acknowledging that we're not going to have any silver bullets, the reality is what it is, and it's just doing its own thing. And we are lucky that we have like some insight into what it's doing. We shouldn't expect any silver bullets. So what I'm trying to say here is that it's going to be hard work. It's like um, it's going to be like we shouldn't expect anything. We should consider ourselves lucky to even have consistent mappings between specific sets of actions to specific results. So we have to be willing to do that as study and practice um, into into what our reality offers. Um, so like given a certain system of, or like a certain problem, we have to be willing to study it critically and know what it offers for it to be maximally exploited. Um, and we talked a bit about the model of computation. So you could have very different kinds of models. You could have a model that, I don't know how you do this, but you could have a model where multiplication is easier than addition, and somehow you'd have to map addition to like multiplication or something like that. But if you haven't heard about it, the architecture that we are running on is von Neumann's architecture. So you have to be like aware of the costs and guarantees this offers. But the if you were to break it down, mostly it's like addition and subtraction, um, and access to memory, like certain addresses of memory comes with a zero, like a cost of, let's say, one. So if you're to like build any software or like any algorithm around it, because you can still break it down all the way to addition, subtraction, and like a few other operations like moving some piece of data to some memory. Your goes back to that. But there's no reason why we couldn't have a different one. It just happens to be the one we use. So you have to understand that model of computation, and then you have to study and practice the kind of repertoire of tricks that have been tested and proven to work on that model of computation. So this is what we call grinding on like lead code, or like actually reading lots of materials. But there's it's not pretty. Like there's what I'm trying to say is you shouldn't expect it to be pretty, because we're just trying to hack our way around everything. So I'll call it a repertoire of tricks. But again, we'll see how these tricks have been organized and how we could possibly make it easier for you to like uh, learn them. So, um, as I said, we've called them repertoire of tricks, but here are some like some known algorithms and data structures. We've not defined what data structures are. I don't think I should. But so let's say it's like a way of organizing data in a way that optimally exploits the way that data is organized, while considering what you're trying to achieve with that data. So these are just a list of um, those tricks. So like you have to know how to sort data efficiently. Um, we have like comparison based and linear time sorting algorithms. You just have to read this. Um, Searching. Um, we have like some algorithm design paradigms or concepts that will like prove themselves to be useful over time, like the divide and conquer paradigm. You have to know about trees and graphs. Trees you can think of as hierarchical, what nodes. So like your family tree, graphs, which are representatives of like networks. So like our road network, you'd want to know how to represent that and like execute some computations on them. Shortest paths algorithms, greedy algorithms, dynamic programming, backtracking, and constraint satisfaction. I'm not going to be defining this. I'm just like hinting them out in case you're looking for um, where to start. These are proven algorithms to learn that will help you. You also have data structures, arrays, lists, strings, hash maps, um, sets, trees and graphs we've talked about. Heaps and priority queues, you can think of these as a way of maintaining order statistics. So like if you have, you can think of it as a class. So if you have a classroom, where people are always sitting according to how they are performing, and after an exam you want to re-rank them, those are what priority queues are. So you might, that way you're able to know that like the kth or like largest or smallest person, um, or like element in the set. We have tries. These are kind of trees, but used with like strings a whole lot. We have disjoint sets. You can think of this as you want to group people by what? By their height, maybe. If you're taller than this, you want to be in a different set. If you're shorter than that, then yeah, stuff like that. So hopefully you can, if you feel the need to, you could like take a screenshot of this or like go back to this video and like go through this on your own, like read through them while searching online. Although I'll also be sharing like some materials that might help you with like a whole lot of this. So I don't know how much time we have. We're almost running out of time. I think I I intend we have like at least one example. We were to do two, but I think one will do. And so we will see what problem you're trying to solve, and then we'll see like what models of or like what approaches we could use and how we could improve on those approaches um, to save on time and energy. So I'm just going to shift here my IDE. Hope you can all see this. Okay.
Yeah.
Awesome. Thank you. So the problem that we're going to be talking about is a bit contrived in that you might not actually apply it somewhere, but the problems that it's like it's a good example of a problem you could face in like actual reality, but it's a bit mathematical. So please just follow through, and if you have any questions, you'll let me know. So you all know Fibonacci numbers, I would hope. So the Fibonacci numbers are defined as, suppose we had a function that takes in a number n. We want to get the number that is given by f of n minus 1 plus f of n minus 2. That's like the general rule. And if you consider that we're going to be reducing these numbers all the way down, we need a point at which we have a definite value. So we're going to say if n is greater than or equal to 2, then give me that. Otherwise, you're going to say just give me 1. That's that's just how we're going to define it. So we can take an example. If I need f of 3, this is going to be f of 2, f of what? 2 plus f of 1. So if to get f of 2 using the same function, I'll just get 1, right? Since we're checking for whether this is greater than or equal to 2, and then f of 1 is just going to be 1 again. So applying that here, I'll get 1 plus 1, which translates to 2. And yeah, if we look through the Fibonacci numbers, that's what we have. So we're going to apply this in like an algorithm. So we're going to say int fib, and then I'm going to take in my n, and then I'm going to say if n is greater than or equal to 2, and return f of fib n minus 1. Otherwise, you just return 1. So we're going to run this, and we're going to run it with let's say 36. 35. And then, so we're going to, let's see. Using namespace std, I'm using C++, but majority of this should be familiar to you. If you're not familiar with C++, that is. So just going to run that. So what I'm doing is I'm compiling it, and then I'm using the time tool to like compute how much time it will take. So maybe I should just compile it first without. So it's actually running, but so that says it takes about 0.12 seconds to compute. Let's give it a bigger number. Yeah, that might take some time. I don't know if it will give us the 45 even. Yeah, so that took 9 seconds. I'm looking like right here, and it gave us the answer. But so if you were to think about this problem critically, what you'd see is that you'd be recomputing a whole lot of these sub problems. So say I had like f of k, or maybe 30. I think it makes sense to use real numbers. So this is going to be f of 29 plus f of 28. If I go to f of 29, I'll be recomputing the f of 28, right? Plus f of 27. And when computing f of 28, I'll also be recomputing f of 27. So it's we are doing a whole lot that we are not supposed to, like that we have already done. So one way that we could improve this is we could possibly save the solutions we already have. So if I compute f of 29, I don't need to recompute it again. I can save it somewhere and then reuse that solution. So we're just going to have, so that whole idea is called memorization. And I only know it because I have studied. That should be the whole point. Like you need to just like be willing to grind. So it's called memorization. We're going to take int n, and then we're going to use kind of a store for the solutions we get. We're just going to call it memo. So we have like a memo here. So if n is greater than or equal to 2, in fact, we could just copy this. That's what we had initially, but there's something we're trying to avoid doing again. So what we could do is we could check in our memory if we already have that value. You'll forgive the syntax. I hope you'll still see like the essence of the solution you need. So if the iterator is not equal to memo.end, that means we have it in stock. Return iterator per second. Otherwise, we have to compute it. So start out with a value. A value becomes this if n is greater than or equal to 2. Otherwise, the value is 1. And then we save it in the memo. And the value. So we had fib 45 taking 9 seconds. We're going to try and see feed memo, and we should make sure we call feed memo here. So that takes 0 seconds. Like instantly, right? Because I think that's just beautiful in itself. Yeah. If we run that with um, without like actually memorizing values, you'll be running nines. And if you think about this in terms of scale, so if you had like this routine running somewhere really low level, like maybe in an operating system, you'd be costing so many people resources, right? While you could actually be taking this approach and having it compute in no time. So there is an even better kind of solution to this, but um, the point I'm trying to drive at is that uh, we need this. You can't go. You can't. I don't. I wouldn't feel satisfied calling myself a software engineer if I didn't have this as a skill. And so that's why fund companies will like really call this out, because in my ignorance, I would consider this a solution, and I wouldn't know like how I would save the company costs if there are like better models of solutions I could use. So yeah, I hope that at least shows you something. Um, yeah. So for the recommended path, I see we're almost running out of time. These slides will be shared. I'll make sure to share them. But first, I would recommend. I mean, most of us might have done Python or JavaScript. I would recommend a language that makes you kind of memory aware, like at least has a hint of memory management. And for me, that's C++. It will allow you to have like full control of what you're doing. So if you at least know C++, there's a book I'm recommending here called Data Structures and Algorithms, Algorithm Analysis by Mark Allen Weiss. If you're into Java, but there's Cedric. It's also just as good a book. And then after that, Algorithm Design Manual. It will take you through like different patterns that we identified earlier. These patterns, and you'll get. It's a really good read. Like even if you don't like enjoy the algorithmic challenges, it's like just interesting. And then you'd have to like practice those skills. I recommend you use LeetCode a whole lot. LeetCode is just has an amazing community. Interested in the end one, I could very easily like keep track of the values I had previously, and then have a new value I'm incrementing. So so we could say for int I is equal to 0, I is less than n, increment I, and then you'd say C is equal to the previous two numbers. And then now I want to make sure that I at least have A is what we are going to be dropping, right? Since this was like the previous value. So I could save A in a temporary value. And then, or rather save B in a temporary value, since that's what we intend to keep. Say my new A is what B was. And then say my B is now equal to what C is right now. It's just moving those values until I get to n, and then I'll return 1. I'll return C as my solution. So we should verify this. Yeah, a few gotchas in like the implementation, but we had this value here as the result, so we should at least expect that value. So And I would expect this would also take 0 seconds, like, because mm, of course it failed because someone is doing something wrong.
I think we are using plus plus I instead of I plus plus.
Um, call out. Although so that would I don't think that's let's just run it, but I don't that's the problem. There's an overflow somewhere.
We are not using temp, I think.
Oh, good point. Good point. That's it. That's it. So the reason plus plus I is in the problem is plus plus I just says increment I, but give me what I was. Um, no, actually it's the other. We're getting out of, but it's just a good thing to know. So increment I, but give me what I was. But this other one is increment I and give me new I. It's just as semantic. If you didn't know the difference, now you do. But this should give us the answer. I would expect this to give us the answer, and it's giving us two. So,
A is equals to temp, and then B is equals to um, the new value.
so say that again.
A should be equals to temp, and then B should be equal to the new value.
Oh, the C.
Yeah.
Right. Who's this? You're doing me some really good work. I would expect implementation becomes murky once you start digging into the details. But so C is equal to A plus B, right? What do we intend to do? What do we intend to happen? We intend for B to be equal to the new B equal to A, right? That's what we intend to happen. And then A should be equal to B. And then we intend for B to equal to C. That's what we need to happen, right? In fact, I think that's because we won't have overwritten any of the values. I'm going to give this another try, but if it fails, there's just something I'm not doing right. It's weird because this is like a very simplistic problem. But I'm gonna leave it at that. I'll post like a better like a corrected version of this. I don't know if there's anyone who has a hint of what's went wrong somewhere, but we don't have to dwell on this. Yeah, I'm still tempted as an engineer to solve it, but it's pointless. So where were we at? I'm not going to be doing the other binary search example, but something to call out, something that intrigued me is if you are to be searching for a value within the range of 10 billion, which is, let's say, the size of the planet, and this value was like randomized. If you are to do like a linear search, so if you are to like search through each individual value, you might end up doing 10 billion searches, which is like silly. Like if you were to do this, it's less than long. say what? I don't know if the compiler might optimize these out. If I do nothing here, let's optimize it out, but let's see if we actually runs it. Yeah, so this is how long it will take you to like search through that list. But if you are to do binary search, and what binary search is, it logarithmically reduces your the time it takes to compute it. You'll only end up with like 33 searches. You're guaranteed within 33 searches you'll get anything you want. So that took us 29 seconds. And this obviously will take no time at all. So that's like how much power just analyzing your problem will give you. But so yeah, I mean, at least you're getting a glimpse of why a company would want someone with those skills, right? Like they're not just testing you. There is real value in having someone with those skills. So when to apply it, um, I mean, so if you have a computationally constrained system, like embedded systems, like Apple Watch is amazing. I don't know how they're able to do whatever they do in there. Um, when you're direct when time directly translates to profit, like trading and stocks exchange, you're competing against other people who are also willing to put in like better algorithms. So algorithms translate to better results and profit. When the security of a system is critical, you might want to establish like computational trust algorithmically. So have a mathematically proven way of conducting business that is secure. So you would need to think about how to make it difficult for someone to break into your system. Um, when you, and this I think is the one that really applies to us when business transactional bottlenecks are realized. So in our work, you might realize that maybe if, authentication is taking time, or like there's a page you have a whole lot of things you're processing and it's taking time. You need to like go down and break it down into the computations that have been taken and then analyze those computations and know what's the best you can do using the knowledge you'll have acquired while reading this material. So save money. Yeah, I think that goes like to all of us. So lastly, yeah, I'd like to be very thankful and grateful for this opportunity to Ryan, Mark, and every other person that organized this event. It takes a lot of planning, I would imagine, outside work. And so I'm grateful for it and grateful for every other person who's like taking their time to attend. Um, and I hope you at least like learn something. And if you have any questions, again, feel free to reach out to me, Coding Edward on Twitter. You have my email there. I go by Happy Potato on our Slack channel. So if you have like an algorithmic problem that you at least tried to solve, please feel free to reach out. Yeah, thank you.
Awesome. Thank you so much, Edward. That was really enthralling. Uh, Now it's time for the Q&A. Does anyone have a question? Feel free to raise your hand or post it in the chat. On the YouTube chat, I can see Brian Howie asking, how could we use algorithmic thinking to help mitigate the queues at petrol stations? Is there an algorithm we can use for that?
That's a good question. And I mean, so like, how about a priority queue? Like maybe there are some ambulances that are stuck out there and they have like a higher priority. Maybe there's some school buses stuck and you'd prefer them to, like, get better service quicker. But I mean, you could come up with all kinds of things, ways to like map a problem to this.
Thank
Yeah.
you. Uh, no other questions that I can see. Does anyone on the call have other question? Okay, it doesn't seem like. Yeah, Edward has shared his contacts, so feel free to reach out to him, email or Slack, and the slides will be available. I'll be sharing them on Slack and on the YouTube link after. And yeah, thank you. Next month we will be having a another talk by Ibutiti. Uh, that will be on. I don't think we've decided on the title yet, but the topic will be around Django performance. So stay tuned for that. Subscribe to the channel. Get notifications whenever there's a live stream. And yeah, thanks for coming, everyone. Have a good rest of your day. Bye.
Yep. Bye.